Good morning, all. This is Dr. Seshagiri Rao, Associate Professor in the Institute of Aeronautical Engineering, Hyderabad. Today, I want to discuss about design of springs. The topic is it's a part of design of mission elements. So, in the previous sessions, already we have discussed about design of mission elements. In this today's session, you will see what is a spring, how do you define a spring, and how many types of springs, and what are the applications of spring, and what are the materials used for springs, and finally we will see the design of springs. So I will give small introduction to design of springs. Here you can see many types of springs are there here. All these springs are used to absorb the energy to avoid shocks and to avoid vibrations. What is a spring? It is a device or it is a mechanical element to absorb the energy due to resilience, which may be restored whenever required. Example, our watch spring. In watch spring, wound to store energy or absorb strain energy to run the watch when regain its original shape. And car springs. So these are examples of springs. In this slide we will see objective of spring. What are the main objectives of spring? So before designing, we have to set objective. What is the main motive of your design? So generally, the springs are designed to absorb the energy to avoid failures of a mechanical system. Here, the first objective is cushioning, absorbing, or controlling of energy due to shock and vibration. So during vibrations, the high amplitude will be occur in the mechanical systems. To reduce the amplitude of a particular vibrating body, you can use these springs, or you can use vibration dampers. The somewhat vibrations you can reduce by using these dampers and springs. For what purpose? To avoid failure of the system. Another objective is car springs are railway buffers to control energy. Spring supports and vibration dampers, already I told you. So what are the applications of springs? So generally, a lot of applications are there. So first one is the springs are used to measure the forces. So measuring forces as in spring balances and gauges. Simple balance. in clocks and starters to store the energy, and then whenever required it will be released. The clock has spiral type of spring which is wound to coil. Already I told you in the previous slide. And then wound to coil, and then the stored energy helps gradual recoil of the spring when in operation to run the watch. The energy gradually recoil of the spring. Nowadays, we do not find much use of the winding clocks. These types of clocks are not seen nowadays. Next one is maintaining contact between two elements. Example, cam and its follower. In our four-stroke petrol engine, we can see this type of arrangement. With the help of rocker arm spring, you can maintain the contact between the cam and follower. In a cam and follower arrangement, widely used in numerous applications, a spring maintains contact between the two elements. So the main function is to control the motion. Another example, governors. The main function is to control the motion. Next application, creation of the necessary pressure in a friction device. So example, brake or a clutch. So you can see this type of necessary pressure in a friction device, brake and clutch, our vehicle's clutch and brake. Here some friction is required. So a person driving a car uses a brake or a clutch for controlling the car motion. By using spring system. The spring system keep the brake in disengaged position until applied to stop the car. For engaging and disengaging. So commonly used spring materials are, so one of the important consideration in spring design is the choice of the spring material. So some of the common materials are given below. I will explain one by one. The selection of spring material is a very important factor in design. So before designing any type of spring, you should select proper material. So example of the various materials are here, hard drawn wire. This is the cold drawn, very cheapest spring material, spring steel. So normally used for low stress and static load. These type of springs are manufactured by using cold drawn process. The material is not suitable at sub-zero temperatures or at temperatures above 120 degrees centigrade. The selection of material depends upon the application. Where it is required. So that's why, remember in our mind, so this material not suitable for sub-zero temperatures and above the 120 degrees centigrade temperatures. Next, oil tempered wire. It is a cold run, quenched, tempered, and general purpose spring steel. So already you know this process already studied in material science. Quenching process, tempering, normalizing, annealing. So however, it is not suitable for fatigue or sudden loads. Fatigue and sudden loads. So wherever the fatigue load or cyclic loads are acting, there this type of material, spring material is not suitable. At sub-zero temperatures and temperatures above 190 degrees centigrade also not suitable. So why? Because in fatigue, whenever the mechanical element or mechanical member is subjected to cyclic loads. So after some intervals, after some cycles, number of cycles, the component will fail. This type of phenomenon is known as fatigue. And sudden loads, so impact loads, sudden impact loads. Example, pressing machine. So best example is a impact testing machine in strength of materials. When we go for highly stressed conditions, then alloy steels are useful. Next material is chrome vanadium. This is a alloy spring steel. Is used for high stress conditions and at high temperatures up to 220 degrees centigrade. So you can use this material for high temperatures. So wherever high temperatures are present, that is maximum is 220 degrees centigrade. It is good for fatigue resistance and long endurance for shock and impact loads. It is withstand for fatigue loads. Under fatigue loads, the component will not fail. So there this material material used for spring. Chrome silica. This material can be used for highly stressed springs. It offers excellent service for long life, shock loading for temperatures up to 250 degrees centigrade. So somewhat increased here temperature 250 degrees centigrade up to 250 the chrome silica. So that's why in designing the selection of material is very important. The selection of material depends upon the type of application. So many types of springs are there. So generally, lot of springs used for engineering services. Here, some springs are shown in this PPT. First one is helical compression spring and flat spring. So bevel spring and torsion spring and lay spring. So these springs are classified under type of load. The springs are subjected to torsion load. So shear stress will be induced. So those type of springs are called as torsion springs. So subjected to torsion or twisting moment. The air compression spring, compression or tensile load, and leaf springs. So also called as this leaf spring is laminated springs. So generally these type of springs are used in automobile sectors. You can find in our vehicle also. Next, helical extension spring and torsion spring and flat spring already over repeated, and a draw power spring and a constant force spring. So these are the many types of springs. So now we will see the important spring is helical spring. So one is helical spring and another one is leaf spring. So now we will see the design of helical spring. So before designing of helical spring, you should know about helical spring construction and then what are the important terminology related to helical spring. It is made of wire coiled in the form of helix, having circular, square, or rectangular cross section. Here shown figure the representation of a helical spring acted upon by a tensile load. A tensile load is acting and a compressive load. The circles denote the cross section of the spring wire. This one. These are cross section of spring wire. This is cross section of the spring. Whenever it is subjected to torsion, T, it will deflect. Some deformation will be occurred in the spring. One is here, tensile force is acting, tensile load. Another one is compressive load. So if tensile load is acting, in that time the spring will elongate. In the compressive load, the coils are very move together, closely packed. The important terms are related to this helical spring. Here, coil diameter and another one is wire diameter. Coil diameter and wire diameter. From here to here, coil diameter. And here, this one is wire diameter small d. And shear force already you know, F and torsion. The terminology of helical spring as follows. Small d represents wire diameter of spring. All units are in mm only. Small this di is inside diameter of spring coil and d not outside diameter of spring. And capital D is mean coil diameter. There is an important parameter in spring design called spring index. So very, very important, this spring index. It is denoted by letter C. The spring index is defined as the ratio of mean coil diameter to wire diameter. So that is, you can write C is equal to capital D by T. So you can find while solving problem spring index by using this relation. It is a ratio of mean coil diameter to wire diameter of spring. So the next one is terms used in compression spring. In design point of view, the following terms are very important. You should know these terms. First one is solid length. What do you mean by solid length? What do you mean by free length? What do you mean by pitch? These all are important nomenclature related to springs. Solid length means when the compression spring is compressed until the coils come in contact with each other. When it is subjected to compressor load, as shown in the previous figure. Then the spring is said to be solid. The solid length of a spring is the product of total number of coils as the diameter of the wire. So you can use this formula. Solid length is equal to N dash multiplied with D. So what is N dash here? Total number of coils, and small d is diameter of the wire. So this product gives solid length of the spring. Next, free length. The free length of a compression spring as shown in figure. So it is the length of the spring in the free or unloaded condition. So it means without load. It is equal to the solid length plus the maximum deflection or compression of the spring and the clearance between the adjacent coils when fully compressed. So you can calculate the free length of the spring by using this expression. See in this figure shown the coil spring, it is in a free condition. So this is a wire diameter and a coil diameter and a pitch. So pitch means it is a distance between one coil to the another coil. So here the length of the spring, the free length of the spring without load and unloaded condition. An unloaded condition, solid length plus solid length LS plus maximum deflection maximum deflection plus clearance. Clearance. So see here when it is subjected to load, so deflection is there. So that is the form of delta. So this length is called as compression length. And then compressor solid. In free condition, first one is without load, unloaded condition, it is loaded and fully loaded. This is known as compressed solid. The coils are joined together. Next one is spring index. So already we have discussed in the previous slide. Ratio of the mean diameter to the coil to the diameter of the wire. Where D mean diameter of the coil and the diameter of the wire. So next one is spring rate. The spring rate or stiffness or spring constant. All these names are same. You can say spring rate, stiffness and spring constant. How do you calculate the spring rate? By using this relation. It is a load for deflection. As the load required per unit deflection of the spring. So mathematically you can write like this. K is equal to W upon delta. So where W is the load and delta is the deflection of the spring. It gives stiffness of the spring. Next one is pitch. The pitch of the coil is defined as the axial distance between adjacent coils in an uncompressed state. So already I shown in this figure. This one is uncompressed state. So what is the axial distance between one coil to another coil? Adjacent coil is known as pitch. The pitch of the coil is equal to free length upon n dash minus 1. So you can use this formula for calculating the pitch. LF minus LS upon n dash plus D. Already you know LF and LS. Free length of the spring, and second one is solid length of the spring, and n dash total length of the spring coils, and D is the diameter of the wire. So by using this relation, you can calculate the pitch of spring. Next one is end conditions of helical springs, compression springs. It plays an important role in designing a spring. The end conditions are suitably formed to apply the loads on the spring. Various forms of end conditions are there. So as shown in figure, first one is plane ends, ground ends, squared ends, and squared and ground ends. So based on this end condition, you can calculate the total number of active coils, active turns. So during application, whenever the spring is subjected to loads, the ends are formed like this. Plane ends, ground ends, and squared ends, and squared and ground ends. So in this table clearly mentioned, so how to calculate the total number of turns and solid length and free length based on the type of end formation. Total number of turns, solid length, free length for different types of end conditions. First one is plane end. The type of end is plane end. The total number of turns are n only. The solid length is n plus 1 multiplied with d. So generally the solid length is n multiplied with d. For in this case the plane ends, you have to add 1. as per present standards. Next one is free length and ground ends. So in examination, they will give, they will mention the type of end is ground, plane, square, like that. So according to the given condition, have to select the total number of turns and solid length and free length. If not mentioned, so you can take it as ground ends. Next one is the squared end. The total number of turns are in this case n plus 2. Solid length is n plus 3 multiplied with d. And the free length is pitch multiplied with n plus 3d. So you must remember this table. Squared and ground ends n plus 2, n plus 2 multiplied with d, and pitch multiplied with n plus 2d. So this is the table related to end conditions. Where n number of active turns, p is the pitch of the coil, and small d is the diameter of the spring coil. Next one is, in designing, you have to calculate the stresses. From the free body diagram, you have found out the direction of the internal torsion. So free body diagram given. So calculate torsion and internal shear force. How do you calculate the torsion? Force multiplied with the distance. Here, force is acting here, and with what distance? The d by 2. That is radius of the coil. So external load acting at the center of the coil. So consider here the compression spring made of circular wire and subjected to axial load W. Here cross section is circular. It may be square, rectangular also, but consider as a square circular wire. In this notations are given. D is mean diameter of the spring coil, small d is the diameter of the spring wire, and N is number of active coils, and G is modulus of rigidity for the spring material, W axial load, and maximum shear stress tau, and spring index, and the pitch of the coil, and delta. So now we will see twisting moment calculation. So axially loaded helical spring. The free body diagram showing that wire is subjected to torsional shear and direct shear. One is torsional shear due to twisting moment. Another shear is due to direct load, shear load. You know that the twisting moment is load multiplied with distance. That is equal to pi by 16 into tau 1 d cube. So shear torsion equation. So by using this equation, you will get the shear stress is 8W d by 5 d cube. So one is capital D is coil diameter and small d is diameter of the wire. So remember this formula. In addition to the torsional shear stress induced in the wire, the following stresses also act. Direct shear stress and shear stress due to curvature of the wire. These two also you must add to the torsional shear stress. The average shear stress in the spring wire due to force, as shown in a figure. So resultant shear stress and the direct shear stress diagram shown in this slide. What is the shear stress at inner edge and outer edge? Resultant torsional shear, direct shear and curvature shear stress diagram. One is due to the direct shear stress, another is due to the curvature shear stress. So we know that resultant shear stress induced in the wire is torsional shear stress plus the secondary stresses, shear stress due to this direct shear and curvature shear. So we will get this equation AWD upon by pi d cube plus 4W by pi d square. So here the positive sign is used for the inner edge of the wire and the negative sign is used for the outer edge of the wire. Since the stress is maximum at the inner edge of the wire. So therefore, you can write the maximum shear stress induced in the wire is equal to torsional shear stress plus direct shear stress. So torsional shear stress already you know and direct shear stress already we have discussed in previous slide. So here, so in order to consider the effects of both direct shear stress and curvature shear stress, a wall stress factor is there. Instead of direct shear stress and curvature shear stress, you can use this wall stress factor, that is K. It is denoted by K. This one is walls. This one factor is introduced by AM wall. So the wall stress factor is K is equal to 4C minus 1 by 4C minus 4 plus 0.615 divided by C. What is C here? Spring index. So the spring index is equal to capital D by D. So that's why I told you the spring index is very important in designing of a spring. Next, deflection. How do you calculate the deflection of a helical spring of a circular cross-section wire? Here we have considered only circular cross-section. Let us assume some length of one coil and multiply the number of active coils as pi d into n, and theta, angular deflection of the wire when acted upon by the torque T. The axial deflection of the spring is equal to theta multiplied with d by 2. So know that torsion equation T by J is equal to tau by R is equal to G theta by L. So what is G? Modulus of rigidity. And theta is angular deflection. Delta is axial deflection. So the theta is TL by JG. J is here polar moment of inertia of the spring wire. So you can calculate the polar moment of the spring wire by using this relation pi by 32 into d to the power of 4. G is modulus of rigidity of the material for the material. Substitute all the values in the previous equation in theta, you will get 16W d square n by gt to the power. A W is load and D is coil diameter and the number of turns, and G is modulus of rigidity for the material of the spring wire, and a small d is diameter of wire. Substituting this value theta, you will get relation stiffness of the spring or spring rate W by delta is equal to G into D by 8 CQ N. Next one is energy stored in helical spring. How to calculate the energy stored? How much energy stored in a spring? So assume that your load is applied gradually and the energy stored in the spring is U is equal to half into W into delta. The stored energy, that is U. So that is another name is strain energy. So deflection here produced in the spring due to the load. The maximum shear stress induced in the spring wire tau is equal to AWD by pi d cube. K is wall stress factor. You know the deflection of the spring, you can calculate by using the above values. Delta is equal to AW d cube n by GT2. Design against fluctuating load. Here substituting values W and delta in equation, U is equal to half into W into delta. Here already W calculated by d cube into shear stress upon 8 kd, and delta also calculated by the shear stress d square and by kd. The volume of the spring wire, length of spring wire, and the cross-sectional area of spring wire. The volume of the spring wire is, it is a product of length of the spring and area of the spring wire. It gives volume of the spring. When load falls on a spring through a height, so that is known as impact load. When it is subjected to impact load or sudden load, then the energy absorbed in a spring is given by U is equal to P into H plus delta, half 1 by 2 multiplied with W into delta. Here W is equivalent static load, the gradually applied load, which shall produce the same effect as by the falling load P. And the delta is deflection produced in the spring when it is subjected to sudden load. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.